Okay, so here is our machine code for this program. Okay, and if I write it back, then save and exit, and then if I run it, dot slash print. Oh, yes, it is printing Ram followed by a new line. Okay, so it is our machine code program is working correctly, right? It is printing Ram, this text. Okay, and if I do the system call tracing, then it is first printing. It is first executing the write system call here, this one, and then the exit system call here, and it is executed with 0 successfully without any error. So our program is working. Okay. Hello friends. So today we will write this program that is written in assembly to in machine code. Okay. So this program will print this text Ram, R-A-A-M Ram, followed by a new line character. Okay, and okay, first of all, let's go with this code. So here the first line is format ELF64 executable 3. Okay, so here the output format is ELF64, and the value 3 marks the executable for Linux system. Okay, so this code is written is using FASM assembly. Okay, so here we have the two procedures. The first one is for the print and the second one is for the exiting. Okay, so first we will so here we are executing two system calls. The write system call here, as you can see here, the write system call, and the exit system call here. Okay, so for printing we will use the write system call. As you can see here in this system call table for x86-64 for Linux. I will post the link of this in the description below. Okay, so here you can see the write system call has the system call number 1, and the system call number 1 stores into the register RAX. It is followed by the 3 arguments. Okay, the first argument is the file descriptor that goes into the register RDI. Then the second is then the second argument is the buff, that means the buffer, the pointer to the buffer that goes to the RSI, and the third one is the count, that is the size of the buffer that goes into the RDX. Okay, so the same thing we are doing, the same thing here. Okay, so here the first line is move EAX, 1. So as we know that in EAX or RAX we will store the system call number. So here the system call number is 1, that is for write. Okay, then in the next line it is move EDI, 1. Okay, so the register EDI or RDI will contain the first argument. Okay, so here the argument number 1 is our file descriptor, that is the file descriptor number 1, that is our standard output file std out. Okay, the next move ESI, MSG message. Okay, so here this is the argument number 2, and this is the pointer to the buffer, the message that we want to print basically. Okay, so this label MSG is here at the last line here. So here we are encoding the bytes for RAM, RAAM RAM, followed by the new line character, that is 10, the ASCII value is 10, and followed by the null character, that is 0. Okay, so here the total number of characters is 1, 2, 3, 4 and 5 that we want to print, RAM/n. Okay, so 5 characters. So the same goes here, move EDX, 5. So in the RDX register, we are moving the value 5. And here the argument 3 is the count, the message length. Okay. Then finally, we do the syscall instruction. That means we are calling the write system call. Okay. Then after that, we will exit our program successfully, okay, without any errors. For that, first we will do move EAX comma 60. So as we know here that RAX will contain the system call number. Okay, so if we go to the system call number 60, that is here. So here this is for the system call exit, and here it will take only one argument, that is the error code, and the first argument will go in RDI. Okay, so system call number 60, and the argument, the first argument and the only argument is 0, that moves into the RDI register. Okay, so here the argument 0 means the error code is 0. That means it is okay, the program is exiting successfully, right? Then finally we do the system call. We do the system call instruction. Okay, that means we call the exit system call. Okay, so if we run this program that is written using FASM assembly, then we will get the output RAM followed by a new line character. Okay, this one here. Okay, fine. Now the challenge here is to write this code in machine code, in pure machine code. Okay, not in assembly. So for this, what we will do is that first we will open our Vim editor with the in binary mode. For to edit the binary file, we will use the binary mode. Okay, and let's say the name of the file will be print. Okay, so it will be a ELF executable file. Okay, so here what I will do is that I will open it using this command xxt. Xxt is the external program here that I will use to write the machine code. Okay, so here the first address will be, the starting address will be 0. Okay, so 0 0 0. Okay, so here 0 0 0, and here what we will write is will be given here. Okay, so this is a PDF document for the ELX64 object file format, and I will paste its link in the description below. Okay, here as you can see here that our ELF, this is our ELF file, executable file. Okay, loadable file here, and the first thing that it will contain will be the ELF header. Okay, and after that it will contain the program header table, and we will have only the one program header table, and then we will have only a single segment. Only three things, we will only contain the three things: the header, the program header table, and the segment 1. Okay, the segment will contain our code and the data. So we are using only the one segment here, as you can see here, for both the code and the data. Okay, the one segment here, and this goes, and our ELF header goes here, and the hidden one, the program header table, will also go into it. So what are these and how they make sense, we will see it right now. Okay, so first we will go with ELF header, that is something that we actually want to code. Okay, so this is our file header, the ELF header. Okay, so here as you can see here, the first 16 bytes at the type of this array is unsigned char. Okay, so first 16 bytes we will go for ELF identification. Okay, so if we go to its description here, the first value from 0 to 15. Okay, so the first value will contain the first four values will, from 0 to 3, will contain the file identification. Okay, it is written here. The EIDENT from 0 to magic number 3 will contain the magic number, and these bytes will be the in hex values only, and this will be the 7F, the hex value for E, L and F respectively. Okay, the first one is 7F. Okay, so first we write 7F here, then E. Okay, for E we'll go here, we'll open our ASCII table I mean. Then for E we have the decimal number 69. Okay, so here I will open this thing, decimal to hexadecimal converter, right, and the value was 69. Okay, so it's 45, so we will write 45 here. The next one will L. This is the magic number basically. Okay, so L, for L we have the decimal number 76. Okay, that means 4C. So the hex byte will be 4C here. Okay, then finally the next one will be F. $70. Okay, it is 46 in hex, right? So we have encoded the magic numbers here. Now the next thing is okay, after encoding the magic number, the next thing is here EL class file, that means the file class. Okay, so EL class here, ident of EL class identifies the class of the object file or its capacity. So table 3 lists the possible values. We will go to table 3, and as we know that our file is a 64-bit ELF object file, so we will encode the value 2 here, and yes, here it is a single byte. Okay, yes, so value 2 will go here, single byte 02. This is a single byte, 02 is a single byte, so these are 2 bytes, that is 7F and 45 respectively, 45 respectively, and this is the second byte, third byte, first byte, second byte, third byte, fourth byte, fifth byte, like that. Okay, now after the file class we have the data encoding, EL data. So EL data specifies the data encoding. So table 4 will list the values here. So we will use the little endian value. Okay, that is value 1. So 0 1, right? Now just a second, okay, so 02 01 is here. Now the next thing will be the file version. Okay, EL version. So EL version, currently this field has the value EV current, which is defined with the value 1. So here the value 1 will go here. Okay, right? Then the next thing is OS/ABI identification, ELOS ABI. So here table 5 lists the currently defined value. So we will go to table 5, and here we will use the value 3 for Linux. As you can see here, we will use the value 3. Okay, so 0103. Okay, after the ABI thing we have the start of padding bytes. Okay, from 9 to 15. This is the size. This is not the last byte. This is the actual size of the ident. Okay, so from 9, going from the ninth byte to the last byte, that is the 15th byte, we will just write 000 for each byte. Okay, So it will go like this here, like this is 1 2 3 4 5 6 7 8. Okay, let me check it here. 1 2 3 4 5 6 7 8. Yeah, correct. So we are done with the padding here. So padding means okay, we have done the padding here. Now we will go to the next thing. After that, after this thing here, E type. Okay, so E type E type, yes, here process independent values for this field are listed in table 6. E type, this is our executable file. Okay, so the value will be 2. And one more thing, E type is its data type is ELF 64 underscore half. So it means the size is 2. We are only considering the size here. So size is 2. That is 2 bytes. So we will write 2. The next line. Okay. So the next address will be 000000010. This is the so after the this will be the 17th byte. Okay, from 0 to 16, this will from 0 to 15 the bytes are here, and this will be the 16 byte. If we use the 0 base value, then this will be the 16th byte. Okay, 16th byte, right? So here we will write 2, and in Latin endian form. So for Latin endian form we will use 0200. Okay, 2 bytes. Cool. Now we have again 2 bytes. ELF half is 2 bytes, right? Yes. ELF 64 half 2 bytes. E machine. So here we will use the value 62 for AMD x86-64 architecture. Like this, our target architecture is AMD x86-64. So he will use the value 62 here. I have found these values on the internet by googling, as these were not given here. So you can just Google for these values for this specific architecture, and the value 62 here. It's in decimal. So first we will convert it into hexadecimal. 62, right? 3E. Okay. And 3E and it's 2 byte, right? So 3E00. It's in little endian form, right? Now the next thing. After machine type we have the E version. It is word, and the word here is 4 bytes. So we will write 4 bytes here. Let me write it down. 4 bytes. And E version. Okay, object file version. So currently this value is defined as 1. Okay, E version as 1, 4 bytes. So we will write it in little endian form again. 1 byte, 2nd byte, 3rd byte, and 4th byte. Okay. Now the next thing is E entry, and it is I think it's 8 bytes, right? Yes, 8 bytes. So E entry is the entry point address. So we will write it later. As you can see that I have highlighted this. This means that we will write these values later. So for now, I will just write 0 as the placeholder. Okay, 8 bytes, right? 8 byte means 1 2 3 4 4 to the 8. Cool, it's done. Now the next, at this starting address, we will write the program header offset, right? So program header offset, what is this? EPH off. Okay, it contains the file offset in bytes of the program header table. So I already know this thing, that the size of the ELF header is 64 bytes. So the offset for the program header table will also be 64. So 64 is in decimal, and in hex it is 40. And okay, and what it is data size ELF64 off or 8. Let me write it down. 8 bytes. Okay, so if I write, okay, let me do it here. This will the answer is 40. So, and it's 8 byte. That means the first byte will be this, second byte, third, fourth, fifth, sixth, seventh, and 8th. Okay, this is in big endian format. And if we write it into the little endian format, then it will go like this. The last byte we will write it here as the first one, followed by this byte, then this byte, then this byte. Okay, so 40 00 00 00 00 00 00 00 8 bytes. 1 2 3 4 to the 8. Done. Okay, now you can just pause the video and check this, just check whatever I have told you to make sense. Okay, okay, now going ahead, we have the section header offset. Okay, as I have told you here that we are not using any section in the loadable file. So yeah, so here this offset will be 0. Okay, so it will again 8 bytes. ELF64 off. Let me check it again. 8 bytes, right? So this section header offset will be all 0, 8 bytes. Cool. Now we'll go to the next address. Now after this one, we have E flags, processor specific flags. Okay, so if we search for E flags here, okay, it means let's keep it default 0. Okay, and what is size? ELF64 word means 4 bytes. Four bytes. Okay, so we will write 0. Okay, now the next thing, ELF header size. As I already told you that ELF header size is 64 bytes. That means 40 hex. Okay, so we will write it as 40, and it is half. Half means 2 bytes. Okay, 2 bytes. So this will go at 40 00, and let me check. Yes, right, 40 00. Okay, now the next thing is size of program header entry. As I don't know about the size now, so I will keep it 0, and it is half. Half means half in 2, right? Yes, 2. I will just start it down. 2 bytes. First byte, second byte. Okay, then next thing I have is this thing, number of program header entries. So we will have only one program header entry, So I will write 1 here. It is again half, that means 2 bytes. Okay, 1, so 0 1 0 0. Okay, then I have, okay, we are done with this number program. Then size of section header entry, it will be 0 as we are not using this. 0. Then number of section header entries and section name, okay, this will also 0. And finally section name string table index, it will also be 0. We are not using these things. Okay, so here we are done with the ELF header, and as you can see here, the size of the ELF header is 40 hex. Okay, and we have left only these two things: the entry point address and the size of program header entry. Okay, I will write them down, that what we are missing, and we will enter them later. Okay, E entry and E program header entry size to fill. Okay, I've written it out. Now the next thing after the file header is the program header table. Okay, for this I will go here. I think it's here. Yes. So the first thing here, I will go to this address. Okay, so the first thing here is the type of segment, P type. So we go to table number 16 for this, and it will be the loadable segment. Okay, so the value will be 1. Okay, and it is of type word means 4 bytes. 0 1 0 0 0 0. Okay, okay, 1 2 3 and 4 bytes, right? Now the next thing is segment attributes, that means P flags, and it will be again 4 bytes. Okay, P flags, table 17. Okay, so this segment will contain the both of our code and the data. So we will have two permissions for this: the read permission and the execute permission. Okay, we can read the text basically, and we will execute them, but we won't need the write permission, right? Because we are only printing the text Ram. So we will add these permissions together. So 1 plus 4 is 5, and we will write 0x5 in 4 bytes. Okay, okay, before proceeding ahead, let's check our executable first. So first we will save it, then we will go to text. We will save our changes in the text mode. Okay, then I will do file print. Oh, so we are getting ELF 64-bit LSB executable, LSB. Okay, then x86-64 version 1 GNU/Linux. Then we are getting corrupted program header size. It's right that we haven't implemented the program header size yet, and there is no section header. That's correct. If I do this thing, then we can see here that the magic is correct. Class is ELX64, data is Little Endian, then version is 1 current, then we are getting the OS ABI Unix dash GNU, then type is executable file, machine is AMD x86-64, then version is 1, entry point address we have to fill it now, sorry, we have to fill it, so we will fill it later. Then we are getting the start of program headers at 64 bytes into file, that's correct. There is no section header, okay. Then flex is 0 and everything is correct. The size of the elf header is 64 bytes, that is correct, and the number of program headers is 1, okay, as we have seen before. Now let's go back to the coding. Okay, so the next thing was p offset in file. So what is the offset of the segment in the file? So we will begin our offset from the 0 from here. So the offset will be 0 and it is of type elf64 underscore off, right? That means 8, right? 8 bytes. So fill it at 0. Okay, now next thing, 4 to the 8, right? Now going to the next thing, it is p virtual address in memory, okay, and it is of type elf64 underscore address, that means 8 bytes, okay. So in this case the virtual address will be 40000, 4 and 5 zeros, okay. So this will be the virtual address and the size is 8 bytes, right? Yes. So this is the virtual address of the segment, means this offset 0 will be loaded address 4000000, okay. So I will write it as okay, this one is this 4000000. So I will write it as in Latin form 000040. And the rest of the bytes will be 0, okay. Okay, then the next thing is again p physical address. It is reserved means you will take it as 0, okay. So and it is of type elf64 address, that means same 8 bytes, okay. So it is 0, so we will fill the rest 8 bytes at 0, okay. Now the next thing, p file size and p memory size, the size of segment in file and the size of segment in memory. We will fill it later after doing the segment part, but after writing the text, basically the code, we will fill it later. So for now we will use the placeholder 0, okay. So these are X word means 8 bytes, so 16 bytes total. Okay, and I will also write it down in my notebook. I will take a note of it that I have to fill first p file size and second p mem size at 6, it is basically at 60 address, right? 60 hex, okay. Now the last thing is p align, it is of type X word, that means add 8 bytes, okay. And P, we will for alignment of segment we will use the value 1000 hex. Okay, so for this one thousand hex, that means 0 0 1 0 okay, 8 bytes, right? Cool. So we are done with the program header table here. As you can see here, we are done with it. And next we will begin with the entry point of this program. So this entry point address will be at here at address, this one will be 70 71 2 3 4 5 6 7 78. So this address will be at 78 hex. Okay, so we got our entry address as for this one. Okay, for 00078. This will be our entry address in the virtual as the virtual memory. Okay, so this is a virtual address, and for this we will write our entry virtual address here. We are just filling the previous unfilled values. Okay, this one entry point address, it is of type ALX64 ADDR, that means 8 bytes. Okay, and first this line for this one, and the second line ALX64 half is 2 bytes. So 2 to 4 and word is 4 bytes. 2 to 4, 4 and 4, 8. So after 8 bytes we will write this address, 8 bytes. Here. Okay, and the address is 78. It's of type it's of type ADDR, that means 8 bytes. Okay, so 8 bytes. So we will fill these entire values here. So 78 0 78 0 0, then 4 0 0, and rest all of this will be 0. Okay, so we have filled our entry address. I will take a note of it. And the last thing in the elif header that was missing was program header entry size. This thing, size of program header entry. This so this is of type elif64 half, that means 2 bytes, and it will come right after this one, right? So elif64 of 8 bytes. Okay, so 8 16 bytes. This for this 2. So this entire line will go here. Then we have eflex elif64 word, means 4 bytes. 4 bytes, 6 bytes, right? 2 3 4 5 6 bytes. Then we have this thing, program header entry size. Yes. So program header, for a program header entry size, as I have previously told you that the program header table begins at 40 right here. Okay, and then our entry point will begin from here. Okay, So this whole size will be 16, 16 into 2, 16 into 3, and this will be 8. So 16 into 3 is 48, okay, and 48 plus 8, 48 plus 8 is 56. So we will do this conversion. 56 in decimal to hex will be 38 in hex, okay, 38, and it was of type half. Half means 2 bytes, okay. So we will fill it as 38, right? Yes, and we are done with it also. Only the two things are remaining here, the p file size and p mem size, that we will fill later, okay. Now let's begin with the code here. Okay, so here first we will write the machine code for this exiting procedure, okay. Means a simple ELF executable file that will simply exit successfully, okay. So here I will comment out this code for printing and this label, okay. Now here the first line is move EAX comma 60, okay. So if you go here, move EAX comma 60. So here EAX is a 32-bit register and 60 is a 32-bit immediate, okay. So if I go here and I open this is the Intel manual. Basically it is the volume 2, that is the instruction set reference, okay. You can download it from the internet. And if I go here, down to move instruction here, okay. So here this is, as you can see here, this move R32 comma immediate 32, okay, this thing here, R32 comma immediate 32, okay. So its opcode is B8 plus RD and ID, B8 plus RD and ID, okay. So ID here is the 4-byte immediate value, okay. So B8 is the opcode byte, okay. And what is RD here? For RD we will go here, okay, 3.1.1.1, okay. And here you can see here RD indicated the lower 3 bits of the opcode byte is used to encode the register operand without a mod R/M byte, okay. The lower 3 bits of the opcode byte, okay. So it will encode the register operand without a mod R/M byte, okay. So basically we will encode the register operand, okay. And in 64-bit mode indicates the 4-bit field of rex.b and opcode 2:0 field encodes the register operand of the instruction. So these 4 fields, the rex.b and the last 3 bits of the opcode, will encode the register operand of the instruction in 64-bit mode basically, okay. So if you refer to the rex prefix in this manual, then you can assume that rex.b will be 0, okay, in this case. So rex.b will be 0 and the last 3 bits opcode 2:0 will encode the register operand of the instruction. So here our register is EAX, okay. And if you go to this table 3-1 here, for EAX the register field is 0, okay. So we basically this is B8, the opcode byte in hex, and its conversion in this in binary is this, okay, 10 111 000, and the last 3 bits, this thing, opcode 2:0. Okay, this will encode the register operand of the instruction. Say the register is 0, register field is 0, so it 000 will encode the 0. Okay, so there will be no any change. Okay, so it will remain B8 only, and we will so B8 plus RD will be B8 only, and the ID will be here this 60. So 60, it is in decimal, 60 in hex is 3C. So I am writing this 4 byte immediate in big endian format, and we need the little endian format, so we convert it to little endian form, and this will be 3C 00 00 and 00. So the final answer or the final opcode will be B8, this one B8, then 3C 00 00 and 00. Okay, so we will write it here, B8 3C to 3 more bytes. Okay, 1 2 3 4 5, 1 2 3 4 5. So we have encoded this instruction. Now the next instruction is move edi comma 0. Okay, move edi comma 0, and if you go to the manual here, then we will see that this will again move R32, edi is 32-bit register, comma immediate 32. The immediate 32 is 0. Okay, so here this is the same thing here. Okay, so it will be B8 plus RD and ID. Okay, so here our register is EDI. Okay, so if you go to this table for EDI, the register field is 7. Okay, this one 7. So rex.b was 0, and the opcode 2:0 will be 111. That means 1 2 and 4 7. Okay, so our B8 in binary was 10111000. Okay, so these last 3 bits from 0 to 2, 0 1 and 2 will encode 111. Okay, these 3 bits, this was rex.b. Okay, so it will become 10 111 and 111. That's in hex is BF. So BF, and the immediate byte, the 4 byte immediate will be 0. So BF 00 00 00 and 00. Okay, so I will write it here, BF 00 00. Okay, 3 bits, 3 bytes, 1 2 3, 2 more bytes, 00 and 00, 5, total 5, right? And this address will be 80. Okay, cool. Now the next thing will be, these are 5 bytes. Okay, 1 2 3 4 and 5 bytes. The next thing here is the syscall. So syscall will be 0f05 in machine. The opcode will be 0f05. Okay, I remember this, 0f05. You can also Google for this. Okay, so we are done with the executing processor here. Now what we need to do is to fill the p file size and p mem size here at 60 hex. Okay, so these were 4 bytes values. Okay, sorry, 8 bytes values. Okay, 8 bytes values. So here you can see the file sizes 80, 81, 82, 83. 80, this is 80, 1, 2, 3, 83 hex. So it will become 83. Oh, sorry. 83, 1, 2, 3, 4. 4 to the 8 bytes, and this will also become 83. Okay, as you can see here, P file size and P mem size are elf x word, elf64 x word, and x word is 8 bytes in size. Okay, so these will be 83 and 83 in little endian form. Okay, now I will save it. Okay, then I will write it back to the text mode. Save and exit. Now I will do /print. Oh, it executed successfully, right? Let's trace the system call here. strace /print. So we are calling the exit system call here with the argument 0, and it is executed with 0 successfully, right? This is our system call that we executed, this one. Okay, cool. And if we see here, the program header, so our entry point is correct, and program header there will be only one that is of type load. The offset is 0, virtual address is 4 and 5 zeros, physical address is reserved, so it will be 0, and then file size is 83 hex. Okay, memory size is same, 83 hex. Flags are R and E, read and execute. Okay, read and execute, and alignment is 1000 hex. Okay, so it is correct. Okay, now what we will do is we will uncomment these lines. Okay, so here the first line for print is move EAX, 1. Okay, so we will go here at 78 hex here. Okay, and here move EAX, 1. Here it was move EAX, 60. So this one is here, move EAX, 1. That means B8, and it will remain B8 for EAX. Okay, B8, and for 1 it will become 0 1 0 0 0 0 0 like that. Okay, just a second. Yes, so we will write it as B8 0 1, basically 5 bytes. Okay, 5 bytes. B8 0 1 0 0 0 0 and 0 0, 1 2 3 4 and 5. Okay, 1 2 3 4 and 5. Now the next line is move EDI, 1. Okay, for this move EDI, 0, and it is 1 here, BF 0 1 0 0 0 0 like that. Okay, here BF 0 1 wait 1 2 3 4 4 and 5. Okay, 1 2 3 4 5 bytes. It will go here. Okay, this will become okay, and I will delete it out. This will go here. Okay, cool. Now the third thing is move ESI, message. Okay, so for ESI, okay, first this is again the same thing. It is a 32-bit register, and it is 32-bit immediate. Same thing here. Move R32 comma immediate 32. Okay, so it will become B8 plus RD and ID. Okay, so B8 hex in binary is 10111100. Okay, and ESI, if you go to the manual, ESI, the register field is 6. Okay, 6. So 6 in hex, so in decimal, what is 6 in binary? 4 plus 2. Okay, that means 110. Okay, 110, and the rex.b will be 0, as I previously told you. So it will become 110. This will be encoded here. Okay, cool. And if we convert this binary back into hex here, it is BE. Okay, so this will be BE. So I will write it as where, here, after this one, right here, BE. And for message, means the address of this label, we will write the placeholder 0 here, as we haven't encoded it yet, right? So 4 bytes, 0, 1, 2, 3 and 4. Okay, now the last second last line is move EDX comma 5. The same, again it is the same thing, 32-bit register and 32-bit immediate. Okay, so it will be EDX will be wait, I have to write it here, and this one was 000. Okay, 10111100. Cool, this was B8. Okay, and here EDX will be 2, that means 010 in binary. Okay, so 2 is equal to 010. Okay, this is 1, this is 2, this is 4. Okay, and rex.b is 0. So we will encode this this thing here, 010. Okay, in the opcode byte, and this byte in hexadecimal will be BA. Okay, so it will become BA. Okay, and 5 means 05. In little endian form it will become 05, and the rest 1, 2 less 3 bytes will be, rest 3 bytes will be 0. Okay, so here we will encode it here, BA 05, 2 bytes less 3 bytes, rest 3 bytes are 0, 1, 2 and 3. Okay, and this will go down here at address, wait, okay, this is correct. Okay, this was BA05, this thing. Okay, now the final thing here is syscall 0f05. And these 4 zeros will go here. Okay, 1, 2, 3, 4. Okay, I will delete these out. Okay, now here we will encode our message here, that is RAM. So R, capital R, its ASCII code will be capital R. 82. So 82 decimal in hex will be 52. Okay, then small a 97, I guess. Small a, yes, 97. So 97 in decimal will be 61 in hex. Okay, 61. Then the next byte is again a, that means 61. Okay, finally is small m. Small m will be 109. 109. 6d. Are we doing correct? 109. 6d. Okay, so it will become 6d. Ram. Then the next line will be 10. 10 means 0a in hex, and the final will be null, that means 00. Okay, and here as you can see the file size is 9f. Okay, this is 90, 1 2 3 4 5 6 7 8 9, 9a, 9b, c, d, e and f. Okay, see, we will update the p file size and p mem size here. 9f. Okay, 9f. And one more thing. Now we will encode this byte for this label. Okay, message. So our message, that means this r, is here at, and this is 90, right? 1 2 3 4 5 6 7 8 9, 9a. Okay, so this is 9a, and its virtual address will be 9a is the offset in the file, and its virtual address will be 40009a. Okay, this will be the virtual address, and we will write it as in little endian form. Okay, where here move esi, where was esi? Let's find it out. This is the system call, and this was, sorry, this was BA05 for move EDS, 5. Okay, and this move ESI, the previous one here. So it will become 9A, then 9A 000040. Okay, 9A 00 then 40. Okay, this will the virtual address for message label. Okay, now I will save it, write it back, save and exit. Now I will run this program. Oh wow, it printed RAM. And if we trace the system call here, so we are executing our write system call here with the fd1. The buffer is ram/n, and the count is 5. Okay, and it is printing RAM. Okay, here. So this write system call is returning the value 5, and then finally that it has written the 5 bytes to the STT out, the fd1, and then it is exiting with 0. Okay, done. And we can see here the file size is 9f now, memory size is 9f now, and the rest parameters are same. Okay, so it is working. Okay, it is printing RAM. If you like this video, then please like my video, and also subscribe my channel, and thank you so much. Ram Ram ji.